to introduce you to Li-Jing Xin, who is a senior research staff scientist and the operational manager of the 17th at the CIBM MRI EPFL section, and she will give a short introduction on Mark.
Okay, so good morning, everyone. So it's my pleasure to introduce Mark. So he has a master in electrical engineering from University of Stuttgart, Germany, and he joined the lab in 2020 February. And with Song Yi together, they are working on a project funded by Swiss National Foundation. And this is an exciting project which attracts electrical engineer work with our physicists together in these years. And they have done amazing work and set up all the framework for this fantastic work. And he will talk about the details later. Thank you.
Thank you.
Thank you, Li-Jing, for the kind introduction, and thank you for welcoming in this setup, this CIBM Breakfast Science seminar. So I will talk today about a fast in vivo assay of creatine kinase in human brain using 31p magnetic resonance fingerprinting. And as I heard, there are a lot of MRI people here actually, so I'm starting, why should we do actually 31p spectroscopy? So 31p spectroscopy has a lot of important information, mainly about the energy metabolites or the energy metabolism with ATP and PCR and PI. There are also other things like the magnesium concentration and the intracellular, extracellular pH level. But we are mostly interested actually in enzyme kinetics, where we have the phosphor flux between PCR and ATP and ATP and PI, which is called the creatine kinase between PCR and ATP and the ATPase between ATP and PI. So the motivation behind our work is that 31p MRS suffers a lot from low SNR. This is mainly because of very long T1 times, very low concentration, and all these things makes it quite difficult or challenging to measure relaxation parameters, and especially the chemical exchange rate, where which is always a little bit more difficult. So we want to use the MRF framework. It is based on the MRI fingerprinting, the SSFP approach by Dan Ma from 2013. I will quickly introduce it on the next slides. And we want to benefit from this great ESSFP SNR efficiency to actually measure the relaxation parameters and the chemical exchange rate. So let's go to this famous 2013 paper from Dan Ma, where she introduced the MR fingerprinting for imaging. And basically, you have a BSSFP sequence where you change your flip angle to a sensitive according to a pattern, and you can also change your repetition time in the SSFP or in the BSSFP, and she combined it with a spiral readout. And what you get is some different patterns regarding or where you are in the brain and regarding like the underlying parameters. In that case, it was T1, T2, and off resonance frequency. And in the middle, we see what is done then with the pattern. On the other side, so we measure in the brain, and on the other side, we create dictionaries where we actually know the ground truth. So for each parameter set, we compute one signal evolution, and then we just have a lookup table actually where we compare the measured signal to our dictionary, and the best match gives us the underlying parameters. And they showed nicely that in MRI, they were able to make very nice multi-parametric map. So they just measured this T1, this T2, and this F-off, and the protein density map just in one experiment. And this is the great benefit, like it's called multi-parameter estimation in the fingerprinting. So now the translation into 31p human brain. So of course now we have some new challenges. So first of all, we also use the BSSFB type of acquisition, and for the start we tried with 1D localization to keep it a little bit simple. And yeah, it has a fast repetition of 18.9 milliseconds, and we have 60 Hertz resolution later in the spectra. For the beginning, we choose a very easy setup, so no chemical exchange rate is included in the model. So we call that a one-pool model, so there are no exchange in between the pools. And we just want to measure, or we just want to estimate the T1 and T2 relaxation times of the main metabolites, the mean of resonance, and we also included a mean V1 scaling factor. So the challenges we had to actually deal with is how to separate the effects. The more parameters you use, actually, the harder it gets to separate them. So you need to advance a little bit your pattern to make it more sensitive to the parameters you want to estimate. With phosphorus, we also commonly use surface coils. They have really poor B1 homogeneity. Then there is this BSSFP issue, which is the bandpass, which of course now we have, if we go over the whole spectra, so in imaging, they try to avoid actually going into this bandpass regions, but we have to deal with it. And of course, still the SNR. So first, we measure the bandpass to actually see how it looks. So we just use two different static clip angles to see what is actually our span, and it's 60 Hertz. And on the bottom right, you see actually where the metabolites are laying in accordance to the bandpass. And for example, you see that the PI actually falls into a stop band. So that was not well designed by us. So there's still some improvement. Yeah. So we tried that on 6 healthy volunteers. We used an inversion recovery and a multi-TE method to measure the T1 and T2 values and compared it to our fingerprinting approach, and repeated the whole thing after a 15-minute break to do a reproducibility analysis. So if we apply such a pattern in the human brain, we get here such a nice waterfall spectra, where you see here the main metabolites like indicated, and then you just take the maximum signal of one, for example, the PCR on the top right, and you try to match it to your dictionary, and that's the solid line which you see on the top right. What you get out is the estimated T1 and the T2 values. So here we see the mean and standard deviation of them. And for PCR, ATP, alpha ATP, beta ATP, and PI on the top, the T1 values, on the bottom, the T2 values. There are still some discrepancies because it's just a very simple model, but still we see it's a very robust estimation in terms of SNR. It's we don't have any changes in the mean values, just the standard deviation is increasing. But for example, in the top, in the inversion recovery, and also for the multi-TE, we see some changes in the estimated values actually for higher SNR. Which is more amazing is actually the reproducibility, which is very good in this method, and actually quite outperforms the inversion recovery method in the T1 estimation. But yeah, so in total, we can say we can use this method to do a fast relaxation parameter estimation of the main metabolites, overall a better reproducibility, and looking at the PCR, we can achieve a 5-fold scan time reduction to 6 minutes. And yeah, this just with a very simple one-pool model. So let's make it a little bit more interesting. So let's add another pool to measure the creatine kinase rate, so the flux between PCR and ATP. So we expand our pattern by part C, where we have 2 asymmetric inversion pulses, where you see the schematics of the pulse profile here on the top right, where first we invert the ATPs. No, first we invert the PCR, and then we invert the ATPs in the second asymmetric inversion pulse. So now we have actually another problem coming up. We have now 6 parameters to fit, and this is, by our knowledge, the most parameters ever fit with the MR framework. And there it's not getting so easy anymore to actually calculate every possible outcome, because with just here 30 in the power of 6, if you want to calculate it for 30 parameter, for each parameter 30 values, you are at the 1 billion calculations you need to do, or this takes quite a lot of time and quite a lot of storage space. So we came up with this nested iteration interpolation method, where we actually break it down in smaller dictionaries, where we just always fit for 1 parameter for a different start value of the creatine kinase rate. And by then we were able to bring it down to n times 990 calculation, where n is actually the number of start values of the KCK, where we choose 5. And at the end, we try to correct actually for all the bias we introduce in between by simplifying it. And this looks like this. So on the left, you see the start value of the creatine kinase rate compared to the estimated creatine kinase rate minus, so the difference minus the start creatine kinase rate. And we found out that actually for the 0 crossing, so if you would actually start with the true creatine kinase rate, you should end up with also you end up in the estimation with the true KCK value. And we use that to correct for the other parameters like the T1 PCR and the T1 of the ATP. We validated that in a simulation. So we changed some parameters to see how this influences our estimations. Actually, it's all quite good. Just the T2 values, we have some quite significant changes, for also significant changes in T2, but so far there are no reports of T2 changes in the phosphor. In the phosphor spectroscopy. So yeah, but we are still working on that so we can conclude it or correct for it. So before we go to the in vivo results, just the work of our master's student, Siren. So instead of using an interpolation approach, we had the idea to actually use a neural network at the end, which of course can take also the other parameters into account and might find a better correction. And of course, indeed, it finds a better correction. So we are really going down here to 3% mean error from 8%. And we see in vivo the comparison, we are much better, which is quite also interesting. Even though we never fitted for T2, we are still able to actually estimate T2 just by training the neural network, with the data. So, but let's go to the in vivo data. We also had 6 healthy volunteers. We used a band inversion transfer approach called ABIT from Jimmy Red and compared it to our method. And again, we did the reproducibility analysis with a test-free test with a 15-minute break in between. So again, here just this group spectra of part A and part C, where of course now we are just interested in the PCR and the ATP, but the others are also there, so they could be used in further studies, further methods improvement. And this is the matching, an exemplary matching of for one starting value. So first we fit for FP1 and the off resonance frequency using this first picture. Second picture is then the T1 of the ATP. Third picture, the T1 of the PCR. And in the fourth picture, we're using part C to actually estimate the creatine kinase rate. And all this is now repeated 5 times for different start values. If we look at the results, we see that the creatine kinase rate is in good agreement between the MRF approach and the APIT. Also, the T1 value of PCR and the T1 of gamma ATP are in good comparison. If we look now over the acquisition time, where we took a different number of averages of our acquisition to do an SNR evaluation, we see that again the MRF provides very steady estimation, so we don't have an SNR dependency on our estimator, which is very nice and which you actually always want to have. And for EPIT, we see there is some deviation, especially for the T1 of ATP. We have some really big changes actually in the value, estimated value. The reproducibility is really great. So we see that even for 4.5 minutes for the creatine kinase rate, we are still below the EPIT overall result. And yeah, the rest of the parameters are also have a really good coefficient of variation. And yeah, so so especially here we can see that creatine kinase rate we can measure in just 4 minutes, and even like if we want to have a very fast measurement, we can still go to 2 minutes with a CD below 20%. So we use that method in a Nestle project. So this actually, I think like 1 year ago, Eugene asked me how many averages we need. I was like, I don't know, maybe let's do 60. So we included an 8-minute protocol at the end of the study, and the study is actually about the effect of circadian rhythm of brain metabolites measured by phosphorus magnetic resonance spectroscopy at 7 Tesla, and the study is actually done by Seaway. And the study design is that people are measured in the morning and in the afternoon, and here you see the experiment protocol, which is repeated in those sessions. And in the beginning, they do a saliva cortisol measurement, and by that, the groups actually get separated in a low morning cortisol and high morning cortisol group. And which is interesting is that in the creatine kinase rate, we see an increase in the KCK for the high morning cortisol group compared to the afternoon compared to the morning. So with this method, we provide a robust and accurate parameter estimation. We showed that the parameters are in a good agreement with the current state-of-the-art method. We have an overall better reproducibility and amazing 4.5-fold scan time reduction to 4 minutes. But even faster is possible in 2 minutes and 15. And we showed that 1D works. That's it from me. Thank you very much for listening.